All right, here we are. I will be here on Monday, of course, but you don't have to be. But I certainly will be, no matter what. So, but yeah, for my calc students, of course, let's try to get this done by next Wednesday. Use that day off to start working on this, and preferably send me some questions by Monday. That would be cool. If you could just send me questions so that I could answer them like with a video or by a post or something. So 3 problems from the book. I said it was chapter 9. I don't know, I must have been looking at a weird old version of the book. It's actually chapter 4. So chapter 4 from the books, whatever the chapter is on isomorphisms, problem 1, 3, and 4, those are not super crazy. This I will explain, but this is essentially find the group of automorphisms on the integers under addition. So when I write this and I tell you that's a group, that's Z with plus as its operation. And then I want you to prove if G is a group, then the group of then this set automorphisms aut G and in G, these are the automorphisms on G, these are the inner automorphisms on G, and I know that doesn't mean anything yet, but it will soon. Prove those are groups. The operation on those groups is composition of maps. So no matter what your operation is on G, in these groups, it's just functions eating each other. And then prove if G is a group, and I have this map alpha from G back to G, and it works like this. It takes an element from G and spits out its inverse. Then this is an automorphism if and only if the group is abelian. So there's 2 things to prove here, right? Prove it this way, and then prove it this way. It's not, it maybe looks heavier than it is. I don't think any of these are super heavy. They're just kind of like little details. And then on this one, I give you this group of 2x2 matrices, and it's a subgroup of the special linear group of 2x2 matrices. So that means that this thing is under multiplication of matrices. So the operation here is matrix multiplication. I would take these, look at a few, multiply them, look for rhythms, prove that to yourself. And I want you to tell me what this is isomorphic to. So I'm not going to give you something that it's isomorphic to. You find that thing, you figure out that thing, and then prove that that is isomorphic. They are isomorphic. And it's a basic group. It's a group we use all the time. So it's nothing crazy. It's not D, it's not a dihedral group. It's a pretty chill group. And I think you'll see it if you just play around with this. Take one of these guys and then multiply it by 1, 1, B, 0. So like make a different one, multiply them together, look at what comes out. I think it'll become obvious at that point. Does that sound okay? I'll give you, yeah? Cool. Got some stuff to do today, and I kind of want to finish up. I want to start off with a really big result, which is kind of cool. And Christian knows about this because we talked about it one day in my office. But it's a really powerful thing that tells you what every group essentially can be thought of as. So let's talk. This is called Cayley's theorem. And then we'll talk about what those things are. Oh my God, theorem. And we'll talk about what those in and ought things are and spend the rest of the hour on that. But Cayley's theorem says this, every group G is isomorphic to a group of permutations. So every group, anytime you see a group, it's really just akin to a bunch of different permutations. And this is going to make so much sense. It's a really interesting way to look at what groups are, a totally different perspective. So first off, just recall, what is an isomorphism? And we can help Abraham here because he missed class and couldn't find the video. So phi is an isomorphism from G to G bar. And why don't you just take a minute and see if you recall what the things are. Karma-free quiz. Maybe it's two things. Depends on how deep granular you get. Give me one of them.
Bijection, which would be 1 and 2.
Yeah, so we'll just do 2 and 3. We'll do 1 and 2. Yeah, so phi is a bijection from G onto G bar. Yeah.
And preserves group operations.
Beautiful. Phi preserves group operations. So what that means is that if I take an A and a B that are in G, then phi of A times B, whatever that group op is the same thing as phi of A times phi of B. And then just keeping perspective here, this is the G operation, and this is the G bar operation. Cool. So what we're gonna do is just construct this thing, and then I've got a cool way to explain it to you, I think. Hopefully, we'll see. So the proof of this is as follows. Let me just make sure I get my feet off the right platform. So we're going to, given group G, construct G bar in the way that I mean it over here. Construct G bar. And the way we're going to do this is we're going to say that G bar is equal to the set of, I got my notes here. The set of transformations, so capital T sub G, for G in G. And what this T of G is a function that works like this. T sub G of input X is equal to Gx. So notice what happens here. You can think of this T sub G takes an element from G, that X, so this is a guy in G, and it spits out a different element in G. But what I'm saying, so this is a very subtle shift, and this is kind of a heavy mathematical abstraction. I'm saying that we're looking at all the ways I can do this, all the different T sub G's that I can construct. I'm thinking of those as separate objects themselves. So this is the collection of all these maps that are possible, that map G back onto itself by simple left multiplication here. Left multiplication. And you can do this with right multiplication in pretty much the same way once we get done. So this G prime, let's just prove the basics first and then show the isomorphism, is a group under composition of maps. And we'll look at like a specific example too after we're done with this. But this is some cool upper abstractions lifting up into a weird space of things that transform the things we're studying. So, all right, so what do we got to show? We want to show G bar as a group. So what do I need to show?
element, inverse is closed.
Yeah, exactly. So we need to show there's an identity. I need to show the inverse property. I need to show closure. And I gotta show associativity, but
Yeah.
I got that from what?
Composition.
From composition of maps. So we've cheesed out with that one a lot. It's not cheese, but it's like, thank God, honestly. So the associativity. Associative. And so this one here, this comes from composition, from the associativity of composition. Composition of maps. So, any suspects for the identity in this group?
Just like the identity permutation, like the one that maps everything to it.
That sounds right to me. So T sub E will be our identity. So for the identity, we claim that T sub E, where E is the identity in G, is the identity in G bar. And so let's just convince ourselves that that's true. T sub E looks like this. And since the identity just returns the thing that's multiplied by, it's just X. Maybe it's obvious from that. Does that if I compose this with any map, it doesn't change it? So yeah, just a real quick, that if I do TE, TG, that's TG, and if I do it the other way, TG, TE, that's just TG. Seems okay? Yeah. Inverse. So inverse. T sub G, so we have G as an element of G, and I want to figure out what that is. Any suspects?
T sub G inverse.
That sounds like a great idea.
And is that because G is a group, so you know that G inverse is part of it? Right?
Beautiful. Yeah, absolutely. So we're going to say T sub G inverse is T G inverse. And we know that G inverse is an element of G because G is a group. And let's prove this to ourselves, that this actually is the inverse of this thing. So if I take TG times TG inverse, and this is composition, and I do that of some element X. It's easier to think about these as with the of X, so we'll just put it there. So what is this? This is TG of TG inverse of X, and we claim this, so we're claiming this. I'll put that there. And then this is TG, let's use our claim, TG inverse of X. So I'm just going through the definitions of using that claim right here. And now I'm going to write out what this is. This map here, TG of something, is equal to G times that something. That's the definition of it. It's that GX. Remember that TG of something is just G times that something. So that's all I'm using here. The something is this. And then this is G times G inverse X, associate identity, because we've got inverses here, EX, and then I get X back. And this is exactly our identity element. So this is equal to T sub E of X. Let me know if there's any troubles with that. All right, and now we just got to do closure. Could you try this? So closure, I'll get you set up. we've got TG composed with TH, and G and H are elements of G. Let's do that of X. What's that gonna look like? Just maybe work it through, just so you get a feel for working with these things. You can work from inside out or outside in. Both will work, get you there just fine. Feeling. You could have done it, I'll do it the other way, just in case that's the way you go. So, or, here I actually, oh, this should have said G there first. Here I did the inside one first, but you could do the outside one first, and this is just G times this dude. And that's actual times, that's group multiplication, that's not a function anymore. Because this is a group element. And then this is something in G because I applied it to X only. And then that's G times HX, and then you just associate again. You get there either way. And GH is back in G because G is closed under whatever its operation is. So this thing is a group. Now, since the one-to-one and onto is pretty easy, so we're going to let phi be the map that takes. Is there any questions? Sorry, I'm just like kind of just plowing ahead. You're good. All right. Cool. Let's let phi be a group from G. Or excuse me, an isomorphism, one-to-one. Well, wait, I can't just assume that. Let's just let phi be this map from here to here. And we're going to show it's one-to-one and onto. Remember that this was literally defined to be this thing here. I almost don't even know if, do you see onto from this? That for every element of G, like to hit anything over here, you had to have taken an element from G to get it. Like I'm literally producing this thing in a way that makes this the only possible outputs, and it's all possible outputs over here. So Christian, I don't know if Christian believes me.
No, I think that makes sense.
Does that make sense? Does everybody feel okay with the onto part? Because we're literally saying that the output of this is for every element here, I'm just creating a T of G over here. So if I want to hit one of these guys, I just pull the appropriate element from here and produce it over here. Yeah? Yeah, okay. Cool. And then one-to-one, let's show phi is, so onto is clear by construction. But one-to-one might not be clear, so let's show phi is one-to-one. And so to do that, I'm going to assume that phi of G equals phi of H, and I need to show that G equals H. Well, phi of G is T of G, T sub G, and this guy over here is equal to T sub H, and I'm going to apply them to an element X. So to say that these two are the same is to say that these two are the same for all X in G. That these transformations give you the same output, no matter what the input X is. Now I go to the definition. This is just G times X equals H times X. How do I show G equals H? X inverse on the right?
Yeah.
Yep. So right multiply by X inverse. Why do I know there's an X inverse?
Because X is an element of the group.
Because X is from the group. Yes. So right cancel to get G equals H. And this is because G is a group. X inverse exists. That's it. So let's understand what this means. So this is like a weird result. The proof's not super deep. Really, it's a lot of kind of the same stuff over and over again. But let's look at how we might view this thing here. So like, how are we gonna do this? So we'll take a chill example, like one of the unitary groups, and look at that and see which one did I mess with here. And we're not gonna do the whole thing. I'm just gonna start it a little bit. One note. This collection T sub G is called, the way we've done it, the left representation of G. And it's only left because our T sub G's are left multiplication.
Is it the same as the like left action group?
Yeah, it is. Yeah, it is. Yes. Yeah, exactly. It's called the left representation of G, and it would be called the right representation if we did this. This would be the right rep. Would be T of G of X equals XG. If that was what your T sub G's looked like, if they were right multiplication. But we're doing the left representation of G. So let's find the left representation of U9, unitary group, modulo 9, everything from 1 to 9 that is relatively prime with 9. So U9 looks like this. 1, that's your identity. 2, 3's not in there because that's not relatively prime. 4 is in there. 5 is in there. 6 isn't in there because that's not relatively prime. 7's in there, and 8 is in there. Why did I pick such a big one? That's why we're not going to do it all. That's right. That's how I got out of it. So is everybody cool with this? And then multiplication is our action here. Multiplication mod 9 is our operation on this group. And let's actually just do a quick, because I want to show you something really cool. Let's start a Cayley table. 1, 2, 4, 5, 7, 8. 1, 2, 4, 5, 7, 8. And let's say that this is the left and this is the right when I multiply, just to make that really clear. So we can go through, you could probably have as much fun doing this. I actually like making these Cayley tables. I find it super satisfying. 'Anything wrong? Oh, and there should be, it's abelian, so you get this nice symmetry down the diagonal. So once you've got one row, you've got that corresponding column. 4 times 4, 16. Mod 9, 7. 4 times 20. Mod 9 is 2. gotta be the other guy I haven't used yet, so 5, 2, 1, 5. I guess we're doing the whole table. Because why not? It's like so close. 25 mod 9 is 7, thank you. Thank you. And then 35 mod 9 would be 9. No, 8. It couldn't be 9. And then 40 mod 9 is 4. So now we might be able to hack it the rest of the way. Oh shit. Yeah, let's just be honest about it. 49 mod 9, 3? No, 3's not in here. 49, 4. Cool. Oh, then there's only one thing left, and that must be 2, 2, 1. There we go. Sudoku. All right, so what is this representation, left multiplication? So Penelope, we're cranking out the U9, the unitary mod 9 group, cool. So let's take a look at some of our transformations. So T1 is going to be the permutation that's just left multiplication by 1. So it's the identity element. And let's write it in permutation form. So if I'm just writing, this is the formula, but if I was going to write out the permutation itself, I'll say T sub 1 equals 1, 2, 3, 1, 2, 4, 5, 7, 8. So I'm using this form for permutation. It just sends everything to itself. It's your identity permutation. Notice, well, let's see, we'll notice in a minute. And then T2 of X is multiplication by 2. So T2 is, that top row is always going to be the same. But I'm going to multiply everything by 2. So that's 2, 4, 8, 1, 5, and then this must be the guy I haven't used, which is 7. Let me stop. Notice how the bottom row is simply the corresponding row here. So this permutation was my identity permutation. Its bottom row is this. This permutation, 2, 4, 8, 1, 5, that's multiplication by 2, 2, 4, 8, 1, 5, 7. It's literally just a way to, this Cayley table is kind of encoding the permutations. It's just, this is the permutation right here. You just, when you multiply through the original elements of the group by one of these guys, it twists them all around. It permutes them. So each one of these rows is simply a permutation of this top row. Can you see that? So let's do one more. Let's do T7. You know, blah, blah, blah. T7 is 7 times X, but that means it's the permutation. This encodes all the multiplications, essentially. 1, 2, 4, 5, 7, 8. And then what's my 7 row? 7, 5, 1, 8, 4, 2. So every Cayley table is just a bunch of permutations. It's a cool way to look at this, is just a shuffling of the elements of the group. That whole thing, there's a whole thing called representation theory in algebra. And when I first took algebra and they started talking about this, I had no idea what it was. Now it seems really easy. I don't think anyone made it sound easy. I think they tried to make it sound like 400 level math. And I guess this is, because frankly, you have to kind of know a lot for any of this to make sense. So that's Cayley's theorem. Groups can be viewed as permutations. And if you have an infinite group, it's just infinite permutations. All right, let's define a couple of things here. So, definition. if phi from G to G, G's a group always, right? Like duh, that's like G, it's a group, is an isomorphism. So notice, it's an isomorphism, it's one-to-one and onto by nature. It is an isomorphism of G onto itself, I'm just going to put that in parentheses, onto itself, phi is called an automorphism. So it's just, this word sounds fancy, but it's just an isomorphism from the group back to itself. In the way that these are, in some ways, right? Multiplying by 2 just takes me back to the group. It's just rearranging things, but it takes me back. Then we got one more. If phi has a specific form, if phi of x is equal to g x g inverse for some g in g, notice how you right multiply by the inverse, you left multiply. So you sandwich the input between g and g inverse for some g and g. Then phi is an inner automorphism. So these have a very special name, inner automorphism. If you're an automorphism and you don't look like an inner automorphism, what do you think we call you? An outer automorphism, that's right. So the outer automorphism, an outer automorphism, it's tough to say, is any automorphism that's not inner. And that can happen often. Is not inner. Well, I don't know if often's the right phrase, but it definitely happens that there are outer automorphism. Good Lord, that's hard. So let's see. Let's start playing with this. I did have some things I wanted to prove first. Okay. I kind of jumped ahead a little bit. We'll come back to these definitions, but at least now we know what the homework means. But we need a couple properties of basic isomorphisms first. So back here soon. But first, basic properties of isomorphisms, which will then be properties of these dudes as well. I think we're doing okay on time. I think so. All right, so properties of isomorphisms. And I'm going to prove, I think, most of these things. So let phi from G to G bar be an isomorphism. G and G bar are groups. We have these properties. And I think we'll just prove them as we go through. The first one is that phi of E is E bar. So this is the identity in G, this is the identity in G bar. Does that make sense? Just notationally? Okay, cool. So proof. Little mini proof. It'll be very informal. First off, I know that phi of E is equal to phi of E times E, because E times E is E. Right? So I'm expanding the E out. Remember that isomorphisms preserve the group product. So this is phi of E times phi of E. So now we've got this equation, phi of E equals phi of E times phi of E. I'm going to multiply by phi of E inverse on both sides, left or right, doesn't really matter. Let's just say right multiply by phi of E inverse. So that's some element in G bar, and I'm taking its inverse. That's why I'm using these braces. It's not phi inverse of E. It's phi of E, the element in G bar, inverted with respect to the group product. This, and what we get is phi of E, inverse equals phi of E, phi of E, phi of E, inverse. And let's do it. What's the left side simplify to?
E.
Where is the left side? Is it in G
Or is it E bar?
It's G bar, right? Because the output, so here, these are elements in G bar, so just keep a note. These are, all this stuff are in G bar, right? So this is E bar equals, now I'm gonna cancel these guys over here, so this is phi of E times E bar. Group these two together, we can associate. And since they invert each other, I get that identity in G bar. But this is in G bar, and this is in G bar, so this is just phi of E by the definition of inverse. So this is like kind of heavy in a way. It's subtle, right? There's subtlety here. We got to be careful. Where am I? Which side, G or G bar? Just keeping that in mind. That's why I want to go through these proofs, because I think there's important things to see. And while I'm erasing, let me know if there's any questions about that. Everybody cool? Penelope, how do you feel about that?
I guess, okay, so.
Yep, cool, let's start.
Yeah, oh, okay. I guess I just didn't read the first part that like E bar is in G bar.
Yes.
So, okay, I was like, how are we getting the E bar?
Does that make sense now?
Yeah, because it's the original part, the Y of equals E bar, which is G bar.
Yes.
Okay.
Yes.
Yeah.
Yeah, it's subtle. Camilla, you good? Abraham? Okay, awesome. All right, property 2. And we're heading up to some stuff that's going to make life easier for our homework. B is for all integers n and a and g, phi of a to the n is phi of a to the n. So raising the input to the nth power is the same as raising the output to the nth power. It's almost like you can move that exponent from the inside to the outside in a way. We're going to kind of proceed inductively here. So first off, a little proof. This will be semi-casual. I'm not going to go, I might go full induction. I don't know. Proof, let's just notice some things. This is like our base case. Phi of a times a. So this is, I should have started, phi of a squared. Sorry, so phi of a squared is phi of a times a. How can I break this apart?
Phi of a times phi of a.
It's phi of a times phi of a, yeah. By using that preservation of the group product. And this is just phi of a quantity squared. So see how that kind of just moves out that way. So let's call that, that's my base case. Cool. So what about phi of a to the n? Well, I'm gonna, this is my inductive step. In some ways, I'm kind of being a little sloppy here. But this is phi of a to the n minus 1 times a. Just kind of pull off that a there. And then because this preserves group products, yeah, I should have probably set up an inductive step here, yeah. I think I might be trapped in the middle of an induction with like no home base. So,
Could you just, yeah, couldn't you just say that that equals phi of
say it again?
can you pull apart a to the n and just say it's phi of a time a, so like a times dot 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 a n times, and then pull it apart that way?
Yeah.
Or do like successive squares.
Yeah, I could definitely. I mean, you see what's happening here, right? Like you definitely see it. Let's just assume. Let's get the freaking inductive stuff in here just to be. I don't know why I tried to pretend like we didn't need it, but that phi of a to the n minus 1 is phi of a to the n minus 1. And now I can use that. Now I got it. So this guy here, by inductive hypothesis, is this guy, and that is, of course, by the laws of exponents, that guy. And I kind of don't want to do inverses because but I'll show you the easy way to do it, and then we can induct. Similar, this is how you cop out as a mathematician. Similarly, for inverses, notice that let's see here. So I guess our phi goes from G to G bar, just as usual. Just want to keep that handy there. E bar equals phi of E. And that's what we just proved up there. That's from A. And this is phi of A times A inverse. And for any A, for all A in the group G. And by the preservation of group products, this is this, and left multiplied by phi of A inverse. And you get at least the basic result here. Left mult by phi of A inverse. And on the left, you're going to get E bar times phi of A inverse equals phi of A inverse on the, and I'm saying it sounds the same, but it's written differently, so it's important to look at the notation. And this is just the identity times the dude I really want. So we see it for the most basic level, that you can bring the inverse out. And then, like, now I'm really gonna cop out and go, and so on for higher negative powers. And so you could do an induction kind of like I've done here. I don't know, I need to see that that's okay.
For the, for B,
Yes.
were we supposed to assume that n was like a whole number?
Yes, n is an integer. N is an integer up there.
Okay, but like for like
I see what you're saying here. Yeah, so for here, this is for n greater than or equal to 1.
Okay.
Yeah, I see what you're saying. Yeah. And then the zero case is just the identity.
But you could like basically repeat the same proof, but for all like
Yes.
negative integers.
Yes,
Okay.
thank you. That's what I needed permission. And by induction, left to the reader, left to you. Yeah, the result follows. It's just need to show it for the negative powers. Just know you can bring any power in and out of an isomorphism. That's the key thing there. I think, yeah, let's see, where's my eraser? There it is. Okay, next one. There we go. Let's see. This one's not bad. For all A and B in G, A and B commute if and only if phi of A and phi of B commute. Let's do this. So this is an if and only if. Let's go this way first. So assume A and B commute. Can you take it the rest of the way? Can you show me that phi of A and phi of B commute? It's a good, like, stepping off place. If you're not sure how to start, apply phi to both sides. Cool. That looked like a good first move. What's the next move?
Split the,
Preservation of the
Yeah.
product, like this.
Yeah.
Does this look good? And we just break these down, and that's literally the result right there. Phi of A and phi of B commute. Yay. The other, oh, no.
Sorry. I
No,
was-
no,
I
no,
did it
sorry, it's never.
differently. I was just wondering if you could do, like, just say one side equals, like, phi of A, B equals what we did, basically, and then say BA equals this, therefore, based on the original equation, the one that we assumed, based on an assumption.
Yes,
Okay,
yeah, you could
That's
do
how
it.
I thought
No,
about
it's
it.
totally cool. You could do it as a two-step thing,
Yeah.
which absolutely.
okay. I know it's a little bit more, but that's,
Doesn't matter, you got it.
okay.
Perfect, you're thinking right. Abraham, do you have a question, sir?
No.
Okay, cool. Let's do the other direction, because it actually is a little subtler, and I'm gonna ask you to help me with the subtle part. So now this direction is we're assuming that phi of A and phi of B commute. Suggestions on the next move.
You could bring them together, like kind of the opposite way you broke up the other
Move
one.
backwards, yeah, like that. So that's phi of AB equals phi of BA. Cool.
Because phi is an isomorphism, you know, it's bijective, and so it has an inverse. And then you could compose each side with phi inverse, and because of the associativity of function composition, you can just like reassociate, it becomes the identity, and then you just get AB.
Yeah, lovely. Or we could just also, so that's all true, that's beautifully said. We could also just say we know phi is 1-to-1. And so if phi of something is phi of something else, then those two things have to be the same, so we could get there the same way, maybe less words, right? So phi is 1-to-1 implies that AB must be BA. Yeah, but what you said, beautiful. And fun to hear as well. I like it. I'm gonna pop a few more up here. So this next one is if G is a cyclic group. I think I might not prove this one, just so we have time to do some examples. But you can find this proof. If G is a cyclic group generated by A, G is a cyclic group generated by A if and only if G bar is a cyclic group generated by phi of A. This one is super important, and even though it's the one I'm not proving, but you can read the proof, you can find the proof. It will take us a while, that's why I'm kind of cutting it out. And you probably should read it through just for understanding. But this is saying that two groups that are cyclic, and you have this isomorphism between them, phi, that if you want to generate this, if A generates this guy, then phi of A generates this guy. And that's like a key observation that's going to make some problems easier. Absolutely. That you want to use a generator, the image of the generator is what I mean. You want to use the image of generators to generate the output. And then E is this. The order of A is equal to the order of phi of A. And this is a super important one, that isomorphisms preserve order. So isomorphisms preserve the order of elements. And you can use that to check if things are isomorphisms. So if you have something and it's sending something to somebody else over here, and the order of this is 3, but the order of this is 2, that's not an isomorphism. That can't be. These two things would have to, and this should be like this. These two things would have to be the same order if this truly was an isomorphism.
But that's not a biconditional, right? Like if order is preserved, we don't necessarily know it's not.
That's true, yes. Yes, sir. Yeah, absolutely. So let's do some stuff now. Let's do some stuff. All right, what example? Let's do some automorphisms. Let's use some of these results to crank this out. So find, compute, aught Z6. I hope that's not one of your homework problems. You're hoping the other way, but this, I'm hoping not. So I'm looking for all isomorphisms from Z6 onto Z6. Now here's some hints on how to do this. First off, figure out your, there's some actually low-hanging fruit. So let's say phi is a map from Z6 to Z6. What has to be true? What one thing do I know phi must map onto the other?
0 must map to 0.
Zero's gotta map to 0, absolutely, that better happen, because the identity has to go to the identity. So this must happen. What is a generator of Z6? Yeah, so let's note, Z6 is cyclic. And in fact, we can write it a couple of ways. Z6 equals that guy. It's generated by 1, and modulo 6, right? Or what else? 5, and I think that's it. Because those are the only two relatively prime to 6. Anything else is going to get you a little subset of that. So what I have to do now is come up to this guy here and make sure that I've got a generator here, and it should, the image of it should generate over here. So our phi, if I can figure out what phi of 1 is, so if we can determine, let me write this out, determine phi of 1, we know phi of any element, because because phi of k is equal to phi of 1 plus 1 plus 1 k times. Yeah? And that's phi of 1 plus phi of 1 plus phi of 1. Now watch this, this is going to get really cool. This is phi of 1 plus phi of 1 plus phi of 1. And there's k of those. So that's k times phi of 1. So now look at what this, now check that out and process it. Because that's powerful here. It basically tells me that once I determine where 1 goes or where 5 goes, I know where everything must go.
And like vice versa, for getting like 5 to 1, you find like 1/5 times phi of 5.
Not one, we don't have a 1/5 because we don't have division. So say which.
I'm trying to think how to go backwards, because I
Oh,
know to get
okay.
from like 1 to 5, you just do 5 of them, but. Because you said if we find 5, we know all of them, but I'm wondering how to go backwards from that one to get 1.
I'm not sure why you're wanting to go backwards. I'm
Because
sorry.
you said if we find phi of 5, then we have all of them.
Oh, yes, for this guy. Let's just focus on this guy for right now, and then we'll get to it. Yeah. I think it'll make more sense once we actually get this going. So where should I send phi of 1?
Yeah, I think 1 to 1.
There's only 2 places to send it. 1 or 5. And this is how the 5 will come in. Does that make sense? Yeah. So phi of 1 must go to a generator of Z6 because 1 is a generator of the input group. And I think this is going to totally clarify it. I wasn't even sure how to answer your question until I got here. So phi of 1 can equal what or what? 1 or 5. And so we've got 2 possible automorphisms. And those are really them. We just got to like write them out. So phi of 1 goes to 1. Let's assume that. So case phi of 1 goes to 1. This is the identity map then. Because now, by that observation, phi of k just goes to k. So that's the identity map. We should always expect the identity map to be an automorphism. So if you're not getting that, you missed one, for sure, and maybe you want to revisit how you're doing everything. Okay, so that's easy. Or, case 2, phi of 1 is 5. So what is phi of k going to be then? 5k. See here? Look here. I'm saying if I know what phi of 1 is, and I'm saying phi of 1 is 5, then phi of k would be 5 times that guy. Let me stop and make sure that seems okay.
If it's addition like modulo though, it would be the same as like k to the 5th, right?
Yes. Yeah, absolutely. But we're in an additive group, so yes. Is that Penelope? Oh, cool. Penelope? Yeah. Okay.
So if we were doing in like Z7 or something and we were going from 2 to 3, would it just be something completely different, like 1.5k?
Yeah, because in Z7, everything's a generator. So you'd have 7 different automorphisms there.
Okay.
Does that make sense?
Yeah.
Yeah. You'd have to have phi goes from 1, phi of 1 is 1. That's the identity. Phi of 1 is 2, the 2x map, the 3x map all the way up to 6x.
Okay. And you only do the 1 mapping to it? You wouldn't do like 2 mapping to 5? You would just
Absolutely.
not do those. Okay.
Exactly. Yeah, we worry about that, and I think that was where the confusion came in when you were thinking. We're only worried about those generators on the output side.
Right, because once we have one, it's just procedurally adding those for.
Exactly.
Okay.
So for every automorphism you create, every isomorphism you create, only figure out what phi of like your generator is gonna be.
Okay.
So these are my two automorphisms right here. So aut Z6 is equal to this, let's call this phi sub 1 and call that phi sub 5 is equal to phi 1 comma phi 5. This is a group. This is a group itself. In fact, it's a group that looks like this. Composition, phi 1, phi 5, phi 1, phi 5. Well, that's the identity maps, all right? So just that's this phi 1, phi 5, phi 1, phi 5. What's phi 5, phi 5? Phi 5 from what? What is phi 5?
It'd be phi 1, right?
It is phi 1, yeah, because it's like phi 25, which modulo 6 is 1. Phi 1. This group of automorphisms is isomorphic to Z2. It's isomorphic to this group here, plus 0, 1, 0, 1, 0, 1, 0, or 1, 0. So there's like this cool structure hidden here, right? All these little structures that we can come back to things we understand. What time have we got? Okay, we got some time. Let me know if there's any questions on that, because we've got some more examples to think about. Does that make this seeming okay? Yeah? Okay, cool. Let's see. Let's do one more example. I want to do like an inner automorphism one. Let's get kind of. Oh God, these are all so complicated. I spent a lot of time doing these guys. Okay, let's do one more. Let's find the collection of inner automorphisms on S3. Your book has an awesome exposition of the inner automorphisms on D4. Totally worth reading through. Foreseeing a longer example that would take like the whole hour probably. But let's find in of S3. So this is the collection of inner automorphisms on S3. And that means I know what they look like. So let's write out S3. So we have that in our hand. So first off, the identity permutation. The permutation that flips 1 and 2. And from here, I just need a rotation. And then this rotation squared. So now I've got 4 elements. I'm going to get the last 2 by composing that transposition with this and that transposition with this. And think of this, this is also the rotations, the symmetries of an equilateral triangle. This S3. S3 and D3 are the same. They turn out to be exactly the same. They have 6 elements each in them. So this guy here is just this flip like that. 1 to 2, send the 1 vertex to the 2 to 1. 1, 2, 3 looks like a clockwise rotation by 120 degrees. And 1, 3, 2 would be 1 goes to 3, 3 goes to 2, and 2 goes to 1. That's a 2 of those clicks. Like that. Sorry, I know the sound effect really helps, but that's a 240 degree rotation. So let's just put this here. This is like a flip. This is a rot by 120. This is rot by 240. this is rotation by 360, any multiple of 360 including 0. And then I'm going to get my last two by computing the flip composed with 1, 2, 3. What does that turn into? And what's this guy turn into? And these would be our last two elements in S3. Let's compute those.
The one's 2, 3, and one's 1, 3.
Yeah, exactly. They're the other two flips. Because this is like rotate, then flip. So you get different vertices being flipped. So this guy here, 1 goes to 2, but 2 goes to 1. So 1 stays fixed. 2 goes to 3. 3 doesn't get touched again. 3 goes to 2. Wait. No, 3 goes to 1. 1 goes to 2. So we get this guy. And then this guy is actually the 1, 3 flip here similarly. So no matter how we got it, we just get this and this. Let's see, wait, I'll do them in the order I found them. 2, 3, and 1, 3. So I've got 6 potential inner automorphisms, and what I have to convince myself of is, are they all the same? Or are there fewer? Are some of them just actually looking different but acting the same? So our aught S3 has at most 6 elements. And let's write them out. So we're going to have phi of epsilon, which just is, it takes an element from the permutation group sigma. It's going to eat it. And it's going to eat it in this way. It's going to take that guy, and it's going to do epsilon, sigma, epsilon inverse. And that's just that, because that's epsilon, and so I haven't touched this at all. The next one is, I'm going to do the 1, 2 of sigma, and it takes 1, 2, sigma, 1, 2, inverse, which is actually just 1, 2 itself, so I could go, oh, well, this is this, because it's its own inverse. Sigma of 1, 2, 3, or phi of 1, 2, 3, acting on sigma, is 1, 2, 3, sigma. That 1, 3, 2 is actually the inverse of the 1, 2, 3. So make a little note, this is 1, 2, 3 inverse. You could check that out. And then we've got phi of 1, 3, 2, sigma, 1, 3, 2, sigma, and then by that same observation, this is 1, 2, 3. And we got 2 more, phi of 2, 3, sigma, is 2, 3, sigma, 2, 3, because that's its own inverse, and then the last one is this dude. Let me stop, and let me know if that looks okay. Because you do have to do this at some point yourself. Yes, sir?
Are these the odd, or is this supposed to be in?
This is the inners.
Okay.
The inners, which will which will actually be odd this time. So you always have this relationship, Cormac. That's a great question. That this is always a subgroup of this, but it's possibly equal to it as well.
I guess odd S3 has at most 6 elements.
Oh, I'm sorry. Yes.
Okay.
Yes. Yes, sir. Yeah, absolutely. Seeming okay? All right, cool. So now I've done this work. I've done all this work, and I can tell you that they're all different. I'm going to spare you the suffering of that. But how would I do it? Let's put up a note here. Now we have to check to see if any of these are the same. And I'm going to put same in quotes because I want you to tell me what I mean by that. What do you think I mean by that when I say they're the same? They all look different.
Are you talking about the inverses being the same in this case?
Oh, say more.
So like for the ones that only have 2 elements in them,
Oh, like these guys here?
Yeah, since they're the same, is that what we're talking about?
Not exactly, yeah, not exactly that, not exactly that. What would it mean for this to equal this?
Oh, okay.
Same transformation, that they take the same inputs and give the same outputs. Does that make sense? They act the same.
Yeah.
So, i.e., does phi of permutation 1, let's just call it, I don't know, mu1 of sigma equals phi of mu2 of sigma for all elements in S3. And so I literally, like what a loser, I guess. I sat around on the couch doing every single one of these. It was actually pretty fun. That's not a loser. Because if I'm a loser, guys aren't doing too great either. You're learning from me. So good God help you. So what I did discern is that these are all the same. And I'll just kind of show you how I went through with this. So I literally examined every single one of them. So I went, okay, phi of, you don't need to do the identity, because that just gives the same input and output. If one of these does that, hey, it's the same as the identity. So I went to this guy here, and I literally, let's see, I put a beta here. And then I made like this little conditional chart over here, just to show you how I thought about this. So if, first I wrote it out, sorry. So this means this thing, 1, 2, 3, beta, 1, 2, 3 inverse, which is that. And then this is equal to, and here I went through all the possibilities for beta. So first off, if beta is a rotation, do rotations commute? Think about the physicalness of this. Do rotations commute? Can you do rotations in any order and get the same result? You can, right? Think about spinning this thing. Doesn't matter if you spin it x degrees this way and then y degrees this way, or y degrees this way, then x degrees this way. Same thing. So because rotations commute, this makes this easy. So there's only 2 rotations, and they're either this or this. What I get out is the inverse of the rotation. So for example, if, or I get out, no, I think I get out itself. So if this beta is like 1, 2, 3, let me show you this. This and this are inverses of each other, and I just get 1, 2, 3 out. If beta is 1, 3, 2, it cancels with this left side and just gets me 1, 3, 2 out. So if beta is a rotation, the output equals beta. So this is how I kind of thought about it. I was trying to think in a more meta way than doing all the raw computations. And then what sucks then are the transpositions. So if beta is 1, 2, what's this going to look like? We're going to get out 1, 2, 3, 1, 2, 1, 3, 2, and then you got to crank that out. I'll let you do it. I'm going to crank out these few here, and once we get these, we got 1 minute left. Tell me what you get, and then we'll whip out these guys real fast. Is that right? 2, 3 comes out? I don't know. I'm not sure we have a consensus, so I'm going to hold off. Tell me if that looks right. It looks reasonable. Let's verify. Look, 1 goes to 3. 3 goes to 1, so 1 stays fixed, so I just closed it off. Don't need it. 2 goes to 1, 1 goes to 2, 2 goes to 3. So 2 goes to 3, and then once you see that, once you get used to these, you're like, I know 3 is gonna go back to 2. It's gonna have to. And then this guy here, let's see, this guy, 1 goes to 3, goes to 2, goes to 3, so 1 goes to 3. I bet the 2 goes to itself, and I bet the 3 goes to 1. What do you think this one is? 1, 2, yeah. It'll go to 1, 2. And it has to, because you have to hit every output. This is a one-to-one and onto map with the thing. So you know you've got to hit everything over here eventually. So it's like one of those Sudoku kind of things again. And then I went through and did that for every single one of these. They were all different. And so what we actually can show is that these are all different. And when you do functional composition of these, what you get is that this group of inner automorphisms on S3 is actually isomorphic to S3 itself. There's 6 things in it, and it acts just like S3, which kind of makes sense because it's built out of things from S3 itself. So what I'm going to recommend, and I know we're a few minutes over, but we're off on Monday, right? So it's all good. I'm going to implore you, spend time with this early. Just do a little bit every day. Like this will be your. Don't do this on Halloween. Go do something fun. Probably Saturday morning could be a wreck. I don't know what your Halloween's like. Mine's going to be. Mine's going to be pretty crazy. So I'm going up with a friend of mine we rented a cabin up by Mount Princeton Hot Springs. It's gonna be good. We're gonna have fun.
So more fun what I got going.
Well, you're welcome to come up if you can figure out what cabin we're in. Well, thank you. Thank you. Don't, yeah, that would be
I
sad.
would try if I didn't know.
I'm sorry. That'd be great. I just like look out. It's like, holy shit, is that Abraham Floyd in there?
Yeah.
How did he find us?
Just show up trick or treat up there for sure.
That's it. Yeah. I don't think they're gonna want 2 grown men trick or treating up there. I think that's called criminal. Possibly.